Now, it's not all easy. The technology is getting harder, and I want to be very frank about that. It's likely that the rate of scaling or the pace of scaling may slow down as we go forward, but it will continue because of those fundamentals that I mentioned about economics. Life was actually pretty good for quite a number of years, especially back in the 80s and 90s. You know, this is a little bit of a complex chart, but it shows a basic transistor, and the way things worked for those decades was called simple scaling. We scaled the horizontal dimensions, we scaled the vertical dimensions, we scaled the voltage, and guess what? We got better density, better speed, better power per circuit, and power density stayed constant. But at some point, we ran into some physical limits. The gate oxide, which insulates the gate from the device, got to be about 3 atomic layers or 12 angstroms, and we couldn't scale it anymore. So scaling had to change, and we couldn't scale to the same levels that we used to in terms of length and width and voltages. And that meant while we still got density improvements, better speed, better power, power density got higher. And that's been a challenge we've been dealing with for the last decade. And in those days of simple scaling, you know, it was great. We scaled all those dimensions, as I mentioned, and the performance got better. When we got into this new arena, when we scaled the transistor, the performance actually got worse. It got worse because capacitance in the device got higher, resistance got higher, and some of the things we did, tricks that we used to improve the performance, actually degraded as we scaled the transistor. So we actually have to put a lot of innovation now in our 32, 22, 14 nanometer technologies to be able to deliver that enhanced performance. So it takes that extra R&D that I talked about. So you see things like, we would continue to scale the transistor, but we have to invoke things like high-k metal gate, going to new types of devices such as FinFETs, these are 3D devices, and other integration innovations. Just to give you some perspective, if you went back before the 90s, you know, we did a little study and said, what elements did we use to make a silicon device? And it was a relatively small number of elements. When we got into that era where we started to reach the end of gate oxide scaling, we had to start to introduce other types of materials, and those are shown in green. Since then, if you look at the ones in purple, as I said, we did a little survey. All of the materials that are shown in purple are ones that we have either put into manufacturing or in development, or ones we've explored in the research phase. And you can see how this has really become a game of materials innovation. And so focus on new materials and new material studies is really a key important element of continuing the technology forward. Now, it's not that technology stops. We've had these kind of disruptions before, but we have to keep innovating. If we look back in the 1980s, we used bipolar technology for making high-performance computing. That was great for basically all of the 1980s, but at some point, that's a very high-power technology. We got to invoke very expensive, very exotic packaging solutions, and at some point, it just got to be too much. And we made that transition to CMOS I talked about, where we could just scale all the dimensions and the voltage. But that ran out of steam, as I mentioned. We got to the gate oxide limit. And what we went into is material innovation, as I highlighted. We introduced things like strain materials, silicon germanium, high-k metal gate. In the case of IBM, we introduced high-performance EDRAM memory, which was a huge innovation. And it basically was worth almost a full technology node in terms of density, power, and performance. Now that era is ending, and we're entering what I would call the 3D era. And it comes in 2 flavors. 3D devices, so these are what I call FinFETs. So rather than having the device horizontal, you now put the key dimension in the vertical direction. And the second is 3D chip stacking. So this is where we actually go vertical. We stack chips, and they can be chips of different types. It could be an RF chip with a high-performance CMOS chip. It could be a memory chip with a logic chip. You can integrate all kinds of different functions, but that gets out of the barriers of horizontal scaling. Now you start to scale in a vertical dimension. Now that will take us easily through the next decade, but what's beyond that? Then you start to get into nanotechnology, multi-chip stacking, and the integration of photonics onto the wafer. But we see a roadmap that will easily take us out well into the 2020, 2030 time frame. But it's going to require continuous innovation to get there. So let me talk about how we deal with that and how we move forward. And it's really two key pieces. One is this focus on material and process innovation, as I mentioned, long-term focus on research and development. And the other is collaboration. We've had a very open ecosystem approach in IBM, partnering with not only other process companies in the industry, but equipment and material suppliers, EDA suppliers, so that we can deliver solutions, complete solutions to the design community. And I'll show an example of the ecosystem later. The capabilities that you need for having basically a fab and a fab ecosystem are highlighted here. We have basically two facilities. One is a 200 millimeter facility which runs older technologies, analog mixed signal, RF, very profitable businesses, very focused on specific consumer applications. And then we have our leading edge technologies which are in a 300 millimeter facility. These go out today to 32 nanometer. It requires packaging capability. You don't have to necessarily have that in-house. We do outsource a significant amount of our packaging work to some of the OEMs out there. We do our own masks, and that's because we are at the bleeding edge, but there are also many companies that provide masks and mask services. We actually second source our masks to a leading mask supplier in Japan. But for a fab, you also need yield and factory automation software. You need a focus on environmentally friendly manufacturing. And then to complete the ecosystem so the fabless companies can design in the technology, you need to have the EDA capabilities. So this is the design kits and the design IP that they can leverage. Fueling all that is research development capability, which I mentioned, and we've had a very collaborative approach for doing that. I want to give you the example of the Albany Nanotech Center. This was kicked off as a partnership between IBM and the state of New York. So New York State was very focused on trying to grow high-tech both development as well as manufacturing in the New York State region. We partnered with them and developed this concept of an R&D facility which is based actually at the University of Albany. So it's actually not on the IBM campus. It's on the university campus. You can see this is quite a large complex. This is our newest building which is going in, and it houses our EUV Center of Competency as well as the R&D Center for 450 millimeter R&D development. But we started this actually with just one building, which was right here, and this campus slowly grew over the course of the last 8 to 10 years. And as we built the capability, we were able to attract key partners. So key leading equipment suppliers such as ASML, TEL, Applied Material, Lam, KLA Tencor, Novellus. They realized that the days where they could do the research and development of a new tool in their own facility were really gone. They needed to be able to partner with a leading edge process technology company so they could try their tool out on leading edge technology. They needed to understand what the problems were that we were facing. And so we have actually in Albany about 30 joint development programs with these companies on developing new processes and new tools that can go into our technology. What do they get out of this? They get access to the ability to run on a leading edge process, and when we incorporate it into our flow and it goes out into manufacturing at IBM or Global Foundries or Samsung or ST Microelectronics, they get manufacturing sales of their equipment. It started out with equipment suppliers, but actually amazing, then it moved into material suppliers because they realized they needed to have access to the equipment. And then Semitech, which was based in Austin, said, hey, this is a great facility and a great ecosystem. We can get tremendous benefits by moving our location there. And they moved their headquarters and their operation into the Albany Nanotech Center. So this started out with one building and basically a small partnership, and it grew. Many more companies came there, many more people. And the number of jobs that it created has been tremendous, far beyond what we started out with. And in fact, the last 3 years, it's more than doubled in the population of the Albany Nanotech Center.